Okay.
Awesome.
Hi, everyone. We're recording this event, so I missed the first 2 minutes, so let me introduce myself again. Hi, everyone. My name is Shuru. I'm today's host for GDG WTM Kuwait, and today we are having an interesting workshop done by Shafiq. Shafiq is from Malaysia, and he's a researcher at Khalifa University. Also, Eid Mubarak. And I'll leave the stage for Shafiq. Please go ahead.
Hi everyone. Thank you, Sharuk, for the short introduction. Yes, I'm Shafiq. I work at Khalifa University. I'm a Malaysian living in Abu Dhabi. Yeah, so we've, I guess, Eid Mubarak as well to everyone. In Malaysia, we say it different. We say Minal Aidin wal Faizin and Maaf Zahir Batin. It's a long thing to translate, but let's just leave it at that. So today, I'm gonna talk about. It's actually a weekend project that turned out to be like a whole learning experience for me. This whole idea of palette transfer. Just to preface the whole talk, so I was kind of curious about the whole concept of clustering. So I had taken it in university before, and I just kept forgetting what the core of it was, and I just wanted to refresh my skills on clustering. And I thought, okay, let me get some interesting data set. And the thing that jumped to my mind was, well, images. Let's see what can we cluster in images. And then I went down a rabbit hole that ended up becoming this whole thing. So let me share bits and pieces of like the journey with you guys. So I guess I will start sharing my screen right now. And of course, if you guys have questions, feel free to put it in the chat. I won't be monitoring it too much, but I hope, Shuruk, you can help me out and maybe just yell at me if there's like a few questions whenever we're on a break or something, because there's going to be points in the slides where we're going to stop and stuff. Perfect.
No worries.
All right.
Quick thing, there is a QA section, if you can see it. I'm going to start the QA, and you can all leave your questions in the QA section, all right?
Awesome.
Okay.
Thank you so much. Let me share my screen. Open display, share. I hope you guys can see. Shiro, can you confirm if you can see the slide?
Yep, we can.
Awesome. Awesome. So let's talk about palette transfer in Python. So the first thing that we want to ask ourselves is, what is the definition of a palette, right? So what is a palette? So if you're someone who's familiar with makeup, then you know it as this like container of colors, right? It's like these little colored powders that you take and you apply onto some area of your body, be it your face, your hands, or whatever it is. From a painting point of view, you have a palette of colors, maybe watercolor, maybe acrylic paint, or whatever it is. But it's basically just a set of colors that you can take and apply onto a canvas, right? Now, similarly, the idea of a palette transfers to computers. So this is an image reduced to its original, to its unique colors, right? So if you had like an image of like a rose or something, or maybe a field with blue skies or something, and then you just took all the unique colors, right? Every single RGB pixel, and then you compressed it down to every unique color. This is what you're gonna get. This is the palette of an image, right? So the whole idea is that a palette is just a container of colors, is the main gist of it. So how do we represent colors in computers? It's a fairly simple thing. So because every color that we see coming out of a device is always something that is represented by light, so we think of it as additive colors. So in additive colors, if you missed art class in high school or in middle school, additive colors are composed of red, green, and blue, and the addition of which combines to form every other color. And at the ultimatum, when you combine the full intensities of red, green, and blue, you get white, essentially. And the absence of which you get black. So in computers, historically, there's different ways of arranging bits for, which bits become red, which bits become green, which bits become blue. In the old days, when they had 8-bit colors, they had this arrangement where you had 3 reds, 3 greens, and 2 blues. Let me turn on my laser pointer. Here we go. Where you have 256 colors. So the number 256 just comes from 2 to the power of 8, which is 256. And similarly, there's different schemes for something that was called high color when
Sujit, are you still there?
all these like digital artistry and everything, but 90% of people who deal with color in their daily lives, I dare even say 95%, use 24-bit colors, where you have 8 red, 8 greens, and 8 blues, right? So equal amounts of each color, equal amount of bits for each color, essentially. It's also known as hex colors. So if any of you have been on something like Friendster or MySpace, God, I'm old, but you might have seen something like hash, FC364A, for example, and that's essentially a representation of a color where these two numbers represent 1 byte, which is essentially 8-bit, for red, for green, and for blue, right? And 2 to the power of 24 gives us about 16 million colors. And that is more color than we really need, because in fact, the human eye, when I was researching this, the human eye can only really distinguish about the order of 10 million colors. So we're at the point where if you're superhuman, then only then can you really pick out these really minute color differences, right? So just to give you an idea, a 3-bit color, right? It's basically composed of these kind of like blocky, sort of like pastelized color, but of course you can do cool things like dithering, which makes it a lot more realistic. But towards this end, where you have more colors, you basically have more information, right? You can represent this image with more fidelity, essentially. Another way of thinking of color is it's existing in this like RGB cube. So in 3-bit color, you have 2 to the power of 8 and 2 to the power of 3, which is 8, and the color lives at the corners of these cubes, right? So red, blue, green, and so on. And then with more and more colors, you get this denser and denser color cube, essentially. Now, with 24-bit RGB, you almost get like this perfect prism cube, which contains every color, essentially. So that's how kind of like color can be thought of as living in 3D space, because you have R, G, and B. Each component is an axis in this 3D universe. So red is in the x-axis, green is in the y-axis, blue is in the z-axis, for example. So how do we represent images? Well, we know how color is represented. So essentially, an image is just basically a 3D matrix. So why is it a 3D matrix? We have n pixels representing the height of the image, m pixels for the width, and then we have 3 color channels, R, G, and B, right? So width, height, and then depth, which is our RGB, right? So it looks something like this. So we have a image here. You have the red channel, the green channel, and the blue channel. Essentially, if you looked at the channels individually without any color, they look like this. But once you combine them, it forms, the actual image. And the way to think of image as data or as a palette is to think of it as containing n by m pixels. Now, the pixels may not be unique, but essentially there's that many pixels inside an image, right? And each point lives in a 3D space, right? So we have pixel 1, the red channel, pixel 1, the green channel, pixel 1, blue channel, pixel 2, red channel, green channel, blue channel, pixel 3, red channel, green channel, blue channel, and so on until pixel MN, red channel, green channel, blue channel. So we can kind of like string it out in this really long matrix, which is like MN by 3 kind of thing, right? So it's a very long matrix usually. And we've talked about RGB being living in this sort of like cube where the axes are determined by the color channel and so on. So you can think of a point as living somewhere within this cube if it's within 0 to 255. Or another way to think about it, if you're like more familiar with like Excel and like seeing tables, for example, you have a column for red, a column for green, a column for blue, and each row is a pixel in the image, right? And because of the values being from 0 to 255, because each number, each channel can have has 8 bits, so you have 2 to the power of 8 possible values, which is 256. It takes 0 to 255, basically any value between 0 to 255. All right, so let's start coding. I'm going to use Google Colab for this, just because everything is on the web and I don't have to, use a lot of my compute power here because I'm already using it for sharing my screen and all that. But essentially, what we're going to do is we're going to have a image. We're going to use PIL or Python imaging library to load the images and view them, and then we're going to use NumPy to kind of convert them into matrices, and then we're just going to play around with it and convert it into like a list of pixels and so on. Okay. So just follow along. I'm going to start from scratch. So if you're fast enough to catch up with my coding, feel free to follow along. I'm going to probably go as fast as I can just to not waste time. All right. So here we go. Not what I want to see. This is what I want to see. Okay, so I'm here on Colab, and the first thing I want to import is PIL, which is the Python imaging library. Actually, from PIL, I want to import something called image, which is just an image object. And I'm also going to import NumPy as NP. That's the canonical way to do imports for NumPy. And then I'm going to define a load image function. So the load image function is going to take a path to the image. And what it's going to do is just use the Python imaging library to open up the image and then just return the image, right? So just a simple function. So if I do load image, and I pass it a path, well, I don't have an image yet, so I can actually upload thanks to Colab's functionality. I wanted to do a poll to load up these images, but just in the interest of time, I'm just going to choose this image. And I'm going to choose another image that's also interesting. This one. Too many similar colors.
It looked interesting. The hockey, yeah. Oh.
It's too many colors. Ideally, I want to find 2 really different colors. Okay. So I think I'm going to choose this guy. So like almost maybe it shares the yellow, but I just want to see what happens if we transfer colors. Okay, that's later down the line, so don't worry about that yet. So I'm going to load color palette 4209. I got these images from this color palette website. I can't even remember where. It's been a while back. But essentially, if you do load image, PIL will display the image for you if you're in like a notebook setting. So not just Google Colab, this also happens in one long 2D matrix. And I'm going to return the image. I'm going to return X, and I'm going to return XU. Okay. So this time I can get X and I can get XU. So for the purposes of these things, right? So we have XU is this long matrix. Perfect. Mean, and just setting the mean of the cluster center, or the new mean of the cluster center to be the new position of the cluster center. By doing that, we essentially want to minimize the variance of a cluster, right? So we minimize the distance between a cluster center and all the points. By doing that, we also get this nice property that we maximize the distance between the cluster. Now, there's like a long proof for it, which feel free to look at it. I'm not much of a maths guy to explain that. But there's this really nice property with k-means clustering where if you minimize the within cluster variance, which is what we're doing with this algorithm, we also maximize the distance between clusters. So the reds and the pinks and the crimsons are grouping together, and the blues and the indigos and the aquamarines are clustering together, essentially, right? And these K colors that we end up with, these new centers, are essentially like the representative colors of the image, right? Because we have, we've gotten the blues, we've gotten the reds, we've gotten the yellows, and these has to be the set of colors that determine what an image should look like, right? So we'll see this a bit more when we start programming it, right? Just to, yeah, that's the video that you guys are supposed to see. So how do we do palette transfer? So once we have this palette, this set of K points that we use to represent the entire image, what we can do is we can just transform pixel. And why? We just want to find what's the closest centroid in that cluster, in the other image, right? So it looks something like this. So let's say I have a new pixel in my second image. I just have to measure the distance between this image and the centers, right? So I look at this guy. Okay, this guy's quite far. This guy's quite far. This guy's still quite far. This guy seems to be the closest. So I'm going to get this guy's color. So it doesn't matter. So whatever color I had here, so let's say it was like brown or something, I'm just going to end up getting purple, right? I'm just going to pull the color that's closest to me. And essentially, I will get the most important colors of the other image, right? So that's essentially what it's trying to do. And then we have to do some reshaping and converting back into Euclidean 8 for the Python imaging library, but that's implementation stuff. So let's try this out, right? Let's try and use the scikits. We're going to use k-means in the scikit-learn package. So scikit-learn does not implement Lloyd's algorithm. It's actually a bit better. I think it's called k-means++. And it's a bit more careful with how they start with the clusters because there's like stuff that could happen if you don't start clusters properly. And we're going to visualize the palette colors as well. So, okay. And then I've got some exercise, but feel free to kind of look at the slides when you have free time and try these yourself. Okay. So let's get back to here. So I have my image X. So this is going to be the source image, right? I'm going to do clustering on this image. And then image Y is going to take all the pixels that are closest in image X, or at least all the centers, or all the K cluster centers that are closest in image X. So let's remove all those. Let's give myself some space. Control and B. Okay. So I'm going to import from scikit-learn dot, I think it's called cluster, import k-means, right? Now, my k-means objects, I can determine how many clusters do I want. So let's say for simplicity, I want 16 colors, right? 16 of the most important colors in this image, right? So I'm going to set that as my KMN object. And then what I can do is KMN.fit on X, U, which is the unique set of colors. You can fit it on X if you want, but X is all the pixels. XU is the set of unique pixels. Let's just do it on the set of unique pixels. And just let it run. So now, all the k-means clustering algorithm is running, and now it's done, right? So to check what the cluster centers are, you can do kmn.cluster centers, and it will actually show you these values, right? So it's not a round number like from 0 to 255, but because it uses an average, So there should be 16 rows here, and each column is in RGB. So what we can do here is we can actually, to get our palette, we can just do round. So it will round it to the nearest whole number. These decimal points, you can kind of, just round them all. It doesn't really matter. It's all for fun anyway. And then you set it as type of np.un8. So why un8? Because for Python imaging library, you need it to be in a specific data type, which is an unsigned integer of 8 bits. So which is what the np.un8 is. It's an unsigned integer 8 bits, essentially. So from a value basically from 0 to 255. Okay, and if we then print out our palette, this is now our set of most important colors. So what can we do with this? We can reshape this into some square or some rectangle and then display it with the Python imaging library. So I'm going to do a palette.reshape. I'm going to reshape the palette. I'm going to reshape the palette into, well, 16 is 4 squared, so I can do 4 by 4 and then by 3. So 4 by 4, my square image, by 3 RGB, right? So if I reshape that properly, I should get, yes, that's what I expect. And then I can do image dot from array. This takes any NumPy array and converts it straight away into a Python imaging library image. And I can set this to, let's say, p image, my palette image. So if I then say p image, I should get my palette image. Okay, it's very, very small because it's only 4 pixels by 4 pixels. But don't fret, we can resize that into, let's make it something big, 64 by 64. And just so we don't get any sampling issues, I'm just going to use the nearest neighbor algorithm to resize rather. And there we go. That's still a bit small for my eyes. Let's go 128 by 128. There, that's better. So, I mean, it kind of really resembles the original image, right? So we've got this really bright pink, right? So let me just bring this image down so that it's closer to the palette. Yeah, so we've got this really bright pink, which is maybe here. And then this darker pink, which is like maybe the shadows, the yellows of the banana and this napkin here. And then the greens of like the palm tree and this thing and the silver of the spoon. Now, it's all basically captured in the palette. So what K-means does is it's basically just taken all these images and averaged out the unique pixels. And it's found that, okay, these has got to be the most important images, the most important pixels, right? So from here, I mean, like if you're like a web designer or something, I know web designers do this a lot. If you draw inspiration from images or something and you're thinking, oh, I wish I can take like the most important colors of an image. This is exactly how you do it. You run a k-means clustering algorithm. And you basically have a palette that you can use for like, like your header is this color, and then your footer is this color, and the background is this color, and so on and so forth. So it's like already something very, very useful that you can already use, right out of the box. And it's only we've only written fewer than 20 lines of code. Yeah, I dare even say, yeah, fewer than 20 lines of code. So this is already great, right? So this is basically our first step. This is palette reduction. We've reduced from 50,000 colors down to 16 colors and kept like the most important colors of the original image. Now, what we want to do is we want to transfer the colors. So what if I had this image and I wanted to take the closest image in the palette here, right? So what can I do? Well, I just compare each pixel in this image onto every pixel in the palette. And whatever color is closest, I just take that color, right? And luckily for us, k-means already kind of does that for us. So because when we do k-means.predict, let's say I predicted on X, right, on the actual image that I actually trained it on. it gives you these whole numbers. And these whole numbers just say which cluster center does it belong to. So for example, this pixel belongs to the 9th cluster center, which is 1, 2, 3, 4, 5, 6, 7, 8. Well, I guess it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So which is this dark color here. So this pixel is essentially mapped to this palette color, right? Now, from these, I can just index the palette, and I'll get all the pixels which are transferred. So if I do palette, and I do fancy indexing on the predictions, I basically get now a set of colors that belong to the palette, but are indexed by the cluster that these colors belong to, right? And now, if I look at the shape, it should be 106,400. I can reshape this back into X shape. And now I should get the original images structure. And if I then do, now this is becoming very, very complicated, but essentially, if you're following along, I just need to do image.from array of this thing, and I should get the transferred image. So this is our original image with all the unique colors, the 50,000 unique colors, and this is the image after we've reduced it, after we've taken, these sets of colors. So you can see it's kind of blocky and stuff. But if you had more clusters, if you had more cluster centers, then you will get a better fidelity in the image. So in the same vein, all we just need to do is replace this X with Y's, essentially, right? So if I take image KMN predict on Y on my transferring image, which is this guy, and then I reshape it back into Y's shape, whoops, but keep the same palette that we've reduced, I can essentially transform Y's colors using X's most important colors, right? And let's see what that looks like. Whoa, okay, right. So clearly there are no blues, right? So it's a very interesting transfer. So clearly there are no blues in this image, right? There's greens and pinks and yellows. No blues. So it's taken the closest thing to blue, which is like this dark green, which is probably these two colors. And all the grays are. Let's have the old image in for comparison. So contextualize everything. So yeah. So now all these blues are now grays and greens and drabs. The yellows, it's done a pretty good job. I mean, because we don't have that many high fidelity yellows. I think if we had more yellows, it'll look better. The fun thing is why the reds are appearing there. Like you didn't expect the red to kind of appear there, but hey, they're the closest color. I mean, the algorithm says it's right. So there you go. That's how you transfer. That's how you reduce, first of all, an image's color palette down into like the most important colors. And then you can then just quickly just take another image, boom, put it into the k-means object, and then get all these other color, transfer the colors of this image, well, at least the most important colors of this image, into this image, right? So yeah, so we've come pretty long way. I hope you guys are following. Shirok, how am I doing on questions and time?
So far there aren't questions, but
okay.
This
Okay.
has been very interesting so far.
Okay. Cool.
I think I have a question. So what you're doing here is essentially like creating the palettes from the images and then remapping them to other images. What happens if the palette is like too small and like the image that you're kind of mapping to doesn't have any close, let's say, colors or similar colors? It will still try to remap the colors to the image?
Yeah, so it will try its best to find the closest color in the cluster center, even if the color was like a million light years away. If that's the closest one, then a million light years away plus one it's going to take that one, So that's
Interesting.
just how the algorithm works. Yeah. Just unique pixels. You don't have to take repeated pixels. We just need a unique mapping. How expensive is that? Well, so what we did was just finding the reduced palette, right? Which is what we did before, right? So what we essentially need to do to transfer every unique pixel from one image to another is to calculate the Euclidean distance, which is what the k-means clustering algorithm does. It just calculates the Euclidean distance, right? The mean or the root mean squared distance, root mean squared value of 2 points. Yeah, essentially what you need to do is calculate an Euclidean distance for each pair. Now, the Euclidean distance is not very expensive to calculate. It's probably doable in maybe linear time or maybe even less. I'm not sure, but it's really easy. It's just a bunch of additions and multiplications, right? But except that we have this pairwise comparison between every pixel from one image to the other, and that gives us a quadratic time. So why is this quadratic? So let's say I have it in the orders of tens of thousands. So even 10,000, let's take a very, very, let's be very, very conservative, 10,000 pixels, right? 10,000 squared is already what, 100 million? Is that right? One with 5 zeros, and then, yeah, so one with 10 zeros, essentially. Is that right? 0,000, add way too many comparisons to make. And in fact, quadratic grows so quickly enough that it actually becomes expensive, which is why sorting is known to be like a holy grail, because it can be done in, comparison sorting at least, can be done in n log n, because it can change, right? You don't have to do, a million squared, which is probably unimaginable. So there's a trade-off, right? So we can do a slow for loop. Look at one pixel, look at n pixels. Next pixel, look at n pixels. Next pixel, look at n pixels. Very slow, but it's memory efficient because you're only looking at one pixel at a time. Another thing you could do is vectorization. So vectorization, if you're not familiar in NumPy, is when you do these matrix comparisons where you essentially can subtract whole matrices together and basically get every pairwise difference very, very quickly. But you risk your laptop RAM dying because somewhere down the line, you're going to have to store all these, for 10,000 pixels, let's say, all these 100 million comparisons somewhere. And that's just going to kill it because you're not going to be able to store 100 million, floating points without your RAM dying, right? So we can do fast way with vectorization, but you don't have enough RAM. So can we find somewhere something in the middle? Can we still do not too slow, but still not overly memory exhaustive? So there is something called Dask. So Dask is this out-of-core computation library, right? So what it essentially does is it's kind of like lazy computation. It doesn't actually do it until you actually say compute, right? So it will try and figure out the best way to kind of form all these computations. And then when you say compute, it will actually start running. Another thing that it does is you can chunk these matrices so that you do bits of calculation at a time. And then at the very end, you kind of like collect them all together. So you don't risk your RAM dying, but at the same time, you can do massive, massive calculations. It's so big that, in fact, we made, for my master's thesis, we actually used Dask to compare like sequences of bacteria together. And we compared like 25,000 bacteria against 25,000 bacteria. So it's the order of that we're talking about. It took about, I think, 2 weeks or so because the calculation that we were doing was very, very expensive. But essentially, it allowed us to do this very, very massive computations, which we wouldn't have been able to do if we had a normal laptop. So that's one of the things that Dask is particularly good at, which is the chunking of data. Virtually, you have infinite memory as long as you keep your chunk small and you have all the time in the world. So if you leave a lot of time and leave the chunk small enough, you virtually have infinite memory. You can do calculations that are immense, essentially. Yeah, this photo came out late. I was supposed to kind of explain this, the pairwise comparison at this stage, but never matter. So what can we do to kind of optimize? Because we're still doing a really, really big calculation, right? So perhaps some optimization might be of interest. Let's try and minimize as much as we can. So we know that colors are duplicated. So let's only compare the unique colors. That's kind of a no-brainer. Let's do calculations in signed 32-bit integer, right? So if your image is small, then the distances that you're expected to calculate are not going to be very, very big, right? They're going to be within the bounds of 4 billion, right? Which is 32 bits. I think 32-bit goes up to 4 billion or so. I think 4 billion, 4 trillion, 4 billion, I think. And you can get away because we're going to do a big sum at the end with the Euclidean distance. So you can get away with using smaller data types, but we can even try 64-bit, to be honest. We don't have to be shy with it because the chunks, if we keep it small enough, we can actually store any a big enough data type. You don't need a square root. So in the Euclidean distance, if you've forgotten your maths class, it looks like this. So you take the square root of the sum of the differences in the red pixel in x, red pixel in y, green pixel in x, green pixel in y squared, blue pixel in x, blue pixel in y squared. So right. So you take the differences between the pixel values, you square it for the red pixel, for the green pixel, for the blue pixel. You add them all up, and then you do a square root. Now, the square root is actually not important, so we can throw that out and still keep important information. Think about distance. As long as the distance is positive, the square root doesn't really matter in essence. So let's say I have from a single point, I have to from a point O to point A. The distance is, let's say, is 16. And from O to B, it's 9. And from O to C, it's 4. Now, if I square root the distances, the order of the distances don't change, right? A is still further away than B compared to O, and B is still further away compared to C from O, right? So as long as the values are positive, we can just throw away the square root and keep the order. And the order is what matters because we're only looking for the closest one, which is C, essentially. We don't really care about B and C, B and A. But what we want to do is essentially just throw away this square root because it's not necessary. So the mathematical term for it is monotonically increasing for positive values, the square root function. So we can just throw it away because it doesn't really matter. And what we can do is once we have this comparisons of unique colors, we can create a unique lookup dictionary. So we just look up all the pixels in X that are closest to Y. And that gives us a constant time lookup. And if we have, let's say, 50,000 items, essentially we can do the transfer. The transfer step is essentially O of n, right? Because it's a constant time lookup for each pixel, and we have n pixels. So yeah, so we have linear time lookup, linear time transfer, constant time lookup. Okay, that's a lot of math. Let's go into coding. There's a lot of tricks I'm going to do, but I'm going to try and explain them to the best of my ability. If you're lost, don't be discouraged. Just maybe rewatch the video. And there's also another video that I did with the assembly, which basically is a rerun of this. Anyway, so let's try and program this, right? Let me get my notes here because things get a little hazy for me after this. Awesome. So we need Dask. I'm going to convert that to a line. Import from Dask dot array, no, import dask dot array as DA. So if you're familiar at all with NumPy, you can just use dask arrays as you would NumPy. So you can do dask array dot linspace 10. It will give you, sorry, 10, 20. It will give you the same stuff as it would in NumPy, but except it's like this representational thing in um, in Dask. So Dask is pretty cool. It shows you what the array looks like. So it's a 50 by 1 array, and it tells you how big the chunks are and how much how much memory you're using and everything, which is like really nice to debug your flow and stuff. But you only get this view in like Jupyter notebooks or like a notebook setting, so you don't get this in like terminals, which is kind of sad. But essentially, what you can do is I can do DA from array, and I can type in XU, right? So I can just basically transfer XU into a Dask array, right? So we know what our XU looks like. It's this RGB, the 3, and then our number of pixels, which is this 56,969. Now it says to me that the chunks take up 170 kilobytes. Fine. We can even change the type to see how that changes. So if I say as type long, np.long, so 64-bit integer rather than 32-bit integer, I can get, so it'll use a lot more memory, but 1.3 megabyte, you can store that in your computer with no problems. Okay, so I'm going to call that XDA, my X array, but as a Dask array. What's important as well is if we apply the chunk. So I'm just going to give it some value like 4096. 4096. You can keep this value relatively small depending on how much memory you have. I have like a 8 gig RAM on my laptop, plus all the stuff that's running underneath. But of course, I'm in a Jupyter notebook. But even 4096 is more than manageable for your computer. So we'll, oops, I think it's chunks. Yeah, oops, chunks. Okay, and if I print out XDA, right. So it's kind of, you can see that it's got these lines now. So it's kind of like, okay, I've broken this this array down into chunks. So the chunks now only occupy about 98 kilobyte. So if I didn't have the chunks, it would basically occupy the entire 1.37 megabyte, which is probably a bad idea because somewhere down the line you're going to do these comparisons. But anyway, I'm going to do the same for YDA. I'm just going to copy this guy actually. For X, for YU, I'm going to keep it 496. Excuse me. Let me take a drink. All right. So what we want to do, we can just display XDA, YDA. What we want to do is every pairwise comparison, right? So for each pixel in X, I want to compare it to each pixel in Y. Now, there's a pretty cool thing that you can do with vectorizations. So if I have XDA here, I can subtract YDA. Because they're of different shapes, I can't just subtract them like that. I have to do something called broadcasting. So if I reshape this into, do I reshape this guy or reshape the other guy? Let me look at my notes. I reshape this guy. So if I reshape this as -1, 1 by 3, I can get this 3D matrix here. So what this says is, it's a little, let me give you a smaller example. So if I have an array, let's say 1, 2, 3, and then 4, 5, 6, and then 7, 8, 9, right? And I have another matrix. So this is, I'll call this matrix A. And I have another matrix B, which is smaller, let's say it's like, so this is a 3 by 3 matrix, and if I have another matrix that is 2 by 3, or 2 by 3, 2 rows, 3 columns, yeah. And let's say it's like 1, 1, 1, just to make the subtractions easy. So I can't just do A minus B, right? What I want to do is basically 1, 2, 3 minus 1, 1, 1, 1, 2, 3 minus 2, 2, 2, 4, 5, 6 minus 1, 1, 1, 4, 5, 6 minus 2, 2, 2, 7, 8, 9 minus 1, 1, 1, 7, 8, 9 minus 2, 2, 2. So that's every pairwise comparison, right? So 3 by 2, 6 comparisons. I can't just do A minus B. That doesn't work. But what I can do is if I reshape B into minus 1 by 1 by 3, I can do that. So I have 1, 1, 2, 3 minus 1, 1, 1, which is 0, 1, 2, right? And then 1, 2, 3 minus, so 4, 5, 6 minus 1, 1, 1, which is 3, 4, 5. 7, 8, 9 minus 1, 1, 1, which is 6, 7, 8. And then for 2, 2, 2, 1, 2, 3 minus 2, 2, 2 is this. 4, 5, 6 minus 2, 2, 2 is this. 7, 8, 9 minus 2, 2, 2 is this, right? So we can do that. And essentially what I've done is do the same for the X and Y matrices, right? I've just basically X subtract Y with this nice reshaping, and now I get all the possible combinations of pixels. So I have all the pixels in Y here, 30,125, and 56,969. So just to show you how insane of a number that is, if you were to keep this in memory, this number times 3, but you know it's unthinkable. You know, it's that is 5 billion. Yeah, you're looking at 5 billion elements inside well, I guess it's a long array, but 5 billion elements, you won't be able to store that in memory, right? So it says to you, it tells you, in fact, you're going to need 41 gigs of memory if you did this thing, right? So if I did at this point, if I can do something called compute, so .compute. If I do this at this point, my computer is going to crash. Even Colab's going to crash. It's not going to have 41 gigs of memory to store, right? But Dask, because we've done this chunking, the most we're going to need at a single point, if you limit it to one worker at a time, is 400 megabytes, which is more than enough, right? I mean, if you have like an 8 gigabyte laptop or whatever, you can store 400 megabytes of memory at one time. So that's the power of Dask. You have this ability to simulate the calculation that you're going to do. It shows you, look, buddy, you're not going to be able to fit this in memory, but I'm going to chunk it for you, and you're going to be able to do it. Give me some time to just do all the calculations, essentially. So what we want to do is calculate the Euclidean distance, right? The Euclidean distance is, as we've seen just now, the square root. We don't need the square root, throw that out. Delta r squared minus delta g squared minus delta b squared. So I have all of my RGB differences in here, in the 3 here. So I have my delta r, delta g, delta b somewhere in here. I just have to square them first. So I have to square. So let's call this as DC, the change in color. And then I'm going to say the squared difference. So I'm going to do dA dot square. In fact, I can probably just put this here. Yeah, I'm just going to square the difference. But I have to target a certain axis, which is this particular axis here. So to figure out what that axis is, you know what? Yeah, let's do this. Let's do this one at a time. Let's just do DC, and let's look at DC.shape. Okay, the axis is on the last one, so I can do dA.square. I want to apply a square. Actually, the square doesn't matter because it's going to apply to all values, actually. So dA.square DC. So now that we have the square difference, we have to sum it across the, because if you look at the equation again, it's sum of delta r squared, delta g squared, and delta b squared. So we have to do dA.sum. and the axis is going to be axis 2. So if we did this right, we should get a, yes, that's what I expected to see. This 56,000 by 30,000 matrix, which is basically now every pairwise comparison. And all I need really is just the closest pixels in here. So essentially, somewhere in this matrix, it's going to say this is the difference from pixel 1 in image X to pixel 1 in image Y. And this is the distance for image X, pixel 1 in image X to pixel 2 in image Y, and so on, up the column, right? And I just really need the minimum value of each column, right? So again, I can just do some fancy stuff here and just do da.min, and I can choose my axis. And I'm going to choose axis is equals to 1, which is going to be the vertical axis, inshallah, I think. Let's see. There we go. So now I have 30,000 colors. Well, actually, I wanted to do it the other way around, axis 0. 56,000 colors, and all of it should be the smallest value, right? And now this array only occupies 400 kilobytes. That you can store in memory, that's not a problem at all. So after all these calculations, then we can actually find all the smallest values. So min is fine. Min finds us the minimum distance, but what we want is the well, I guess the position in the pixels that is of the minimum value. So the argmin. So essentially, we don't want to use min here. We want to use argmin. So argmin gives you the index of a particular value. So if I do np.argmin of a list, let's say 9, 5, 3, 2, 7, 10, it's going to say 3. Yeah, because on the third position, 0, 1, 2, 3 is the smallest value. So what I want to do is find the smallest index, right? So that will tell me the position of the pixel in the image, right? Now, let me just clarify what I want to do. I want to get a mapping of X onto Y. So is it better to get the pixels of Y, or is it better to get the pixels of X? I think it's better to get the pixels of Y. So I'm going to change this to 1. So it's going to be 30,000 colors, but each of the 30,000 colors is an index of a pixel in X. Yeah, that's what I want. So I can call this my mapping. That's the term I use in this notebook. And okay, let's call this my before the argmin, everything up to the argmin. Let's just name these things so we don't get confused. This is our pairwise distance matrix, basically. Pairwise distance matrix, and my mapping is argmin of the pairwise matrix axis 1. Okay, so awesome. Now we're ready to do the calculation. I'm gonna import something called progress from, I think it's called what is it? I forget. From dask.diagnostics. From dask.diagnostics, import progress. That just tells you how far along the calculation is going, just so we can monitor what's going on. So so if I just say with progress bar, I can do mapping dot compute, and I will return the output, which is this array, as let's just call it mapping, because we're not going to use this this matrix anyway. So boom, there we go. And there it goes. At this point, you go and grab coffee, or you go to the bathroom, or watch some TV, look at an ad on something on YouTube for a few seconds, and then come back and it's done. So it does take a while, depending on how big your matrices are. So because we had to do like I said, 5 billion calculations chunked in pieces of 4096. Looks like it's gonna be done within a minute, but it usually doesn't take longer than minutes, unless you have something very, very big, or if your computation somewhere in here is very, very expensive. But as long as you're doing like NumPy calculations, usually it's very, very fast. So 48 seconds, perfect. Now I have my mapping vector, and the mapping vector just says, okay, for pixel 1 in image Y, use pixel 3 in image X. For pixel 2 in image Y, use pixel 3 in image X, and so on and so forth, right? So now we have the mapping. It basically looks like our clusters thing that we did earlier. So all we need to do is just XU, and if we index mapping, we get essentially the transfer of XU onto mapping. So if I take a look at the shape here, it's going to be 30,000, which is the shape of YU, but it's going to have all the colors of XU, right? And all that's left is to just reshape it back into Y shape. And if you're ahead of me here, we have image.fromArray, and we can transfer. Bismillahirrahmanirrahim. Nope. Where did I go wrong? Yeah, because this is only, sorry. Yeah, this is only the unique colors. I need to, yeah, sorry, my bad. I need to find, I need to create a dictionary first. This is later on. So these are all the colors that YU should take from XU. And what I need is a mapping, right? Am I missing something? Let me look at my notes. Yes, I just need to have a mapping from YU to XU mapping. So I will create a dictionary. I will create my lookup table, which is a tuple of the pixel, change it to list, Q for PQ in zip YU XU mapping. Okay, there's a few things. P have the values of Q, which is the effects. Okay, let's take a step back. Let's have a look at again at XU mapping. The mapping, remember what the mapping is? It's just, it tells you which pixels in XU, which pixels in XU do I need to take for this pixel in YU. So at pixel 0 in YU, I take pixel number 3. At pixel 1 in YU, I take pixel 3 from XU. And XU mapping is just basically the values of those pixels in XU, right? So it's still the same size. I've just taken the values of XU. And the lookup table, what I'm going to do is just map all the values of YU. So if you remember what YU looks like, so YU looks like this, but essentially what I want to create is a mapping from 004 to 310, 005 to 310, 007 to 310, and so on. So I basically have this, all the unique colors in YU are going to take all the colors here, which are the colors actually in XU that are closest to YU. I hope that makes sense. If it doesn't, well, good luck. No, I'm kidding. Let's ask a question if you're still a bit confused or if you're not following. But let's drop the mapping lookup table, and we should be able to see if we print out the mapping lookup table. It looks something like this, right? So all the keys here are values, are arrays essentially. So whenever I see 004, I should take 310. If I see 005, I should take 310. And you're going to see a lot of these repeats because some of these colors, that's the closest one they're going to get, right? So it's common to see repeats and stuff, so don't worry about it. Okay, cool. So from here, I can then transfer. Right. So let me just make an array. Let's call this y transfer, right? YT. I'll make it an NumPy array of mapping LUT p dot to list. Well, tuple p dot to list. 4p in YEU. Did I get that right? In Y, rather. So for all the pixels in Y, which is all the non-unique pixels, basically all the pixels in Y, I just basically apply this mapping and then convert it back into an array. So if I have a look at Y underscore T, I should get that. Perfect, 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 perfect. This is the home stretch. All we need to do is just image.fromArray YT, reshape it as Y shape. And if everything, I think everything should go well here. There we go. So now this is the transferred image of YU onto all the pixels in XU. So let me just draw up XU again, just to get context. We don't need this anymore. So you might be thinking like, whoa, that's pretty cool. Like, I didn't expect that blue, or like that blue. Like, is it blue? So there are shades of colors that, because we are contextual, our brains have learned patterns to detect things that are important. We think of the leaf as green, but really there are dark shades of, I don't know, certain colors that really looks really bluish. And take yeah, so that's pretty much a whole palette transfer. You can transfer all the colors of one image onto another image, and it will live vicariously of of the source image, which I think is pretty cool. So yeah, I mean that's pretty much it. That's whole palette transfer to some extent. If so, Shuruk, how are we doing on time, and how are we doing with questions and stuff?
There isn't questions right now, but
Okay.
I think you're fine with the time. For some reason, not many attendees are showing up, but I do have a question. Okay.
Okay.
So there's a lot of math that's going on here.
Okay.
Yeah, a lot of math.
Yeah.
And I got a little bit lost with the mapping that you did with the dictionary. So what you're doing essentially here is that you're trying to map the unique pixels from X to Y, and then you're creating tuples as your reference for the keys. So the tuples are from what exactly? So like P, Q, Q. Yeah, that was a little bit confusing.
So let's just have a look at this. So P if I take YU0, for example, that's one of my P's, which is 004, right? Okay. And YU is the set of unique pixels in Y, right? So in this blue image, right? All the unique pixels in Y. Okay, so far. And XU mapping is also the set of pixels belonging to this image, but that has been taken from XU. Because we've done this calculation, right? And we found what's the closest color in XU0, in YU0 to all the pixels in XU. Does that make sense? Right, so that's our Q. Yeah. So our Q is basically our transfer ring color. Our P is our source color in Y, right? So this is the source color in Y. Q is the transferring color in Y that we've taken from XU. Okay, so Q here again is the transferring color. P.toList here, we have to do this because Python doesn't like storing NumPy arrays as keys inside a dictionary. So we have to convert it into a tuple. But essentially what the mapping lookup table says is, oops, not lust. What the mapping lookup table says is, if I have a pixel of this value in Y, in the original Y image, I should take this value instead. Now, this value, where does it come from? It comes from XU. It's the closest value to 004 in XU. There's no other closer value. Okay. And essentially, it's a mapping from all the unique pixels in YU to all the closest pixels in XU. So anything that's to the right of the colon is pixels in XU, pixel values in XU. Anything to the left of it is all the pixels in YU, essentially.
Okay, interesting.
That's all the mapping.
Okay. Another thing maybe I've missed in the middle, the reason why you're using the unique values and you're using the unique values, but at some point you started using non-unique values, which is the line right after it, where you take P and Y. So what was exactly the relation here, so I could understand a little bit?
So Y is all the pixels in Y, right? In the image Y. The reason why we do this is because so Y, we can reshape it back into Y shape and then do image.from array. So I can do this and get the original image, right? Because it contains every single pixel in Y, right? With the duplicates and everything. So, but in the unique set, I cannot reshape it into Y, into this image again, because it's a unique set, right? We've lost the spatial information of the image.
Yeah.
Does that make sense? So what I do here is, for each of the original pixels in Y, I map the colors that it's supposed to take in this lookup table.
But isn't the lookup table only made of the unique values? So what happens to the non-unique here is that, do they still get matched up?
So let's say I have in the image, for example, I have, well, let's look at the lookup table again. So let's say I have in the first row of the image, I have 004, 004, 004, 004, 004, all across the entire row of the of the image. So what it's going to do is, it's going to be like 310, 310, 310, 310, 310.
Oh, okay. Now I get it. Okay. Makes sense.
So this is just basically like, okay, I see this value, I'm going to take this
and
value.
You just, like,
I see this value. So it's just basically a lookup. Yeah. Okay. So that's why we say that the transfer ring is constant. It's linear time, because we just have to compare every pixel to the key in the dictionary, and because dictionary is constant time lookup, so essentially you have k by n. Yeah.
Okay.
Okay.
Makes sense.
Awesome. So this is great, right? I mean, we can transfer essentially every pixel in one image into every pixel in another image. So where do we go from here? Can we do better? Ooh. Well, let's talk about this color space, right? So I'll bring you guys back to this whole RGB cube idea. There's something weird about this RGB space, actually. There are a lot of colors which are close together, and others which are like, no. Okay, the transitions are working. So some colors are very close together, but they're not visually similar. Now, what does that mean? There are, let's say I see a green in the RGB space, and I see another green. It might not actually be as close as you think in RGB space, although it looks visually very, very similar. So here's the demonstration. So I've got these two pictures here, right? And I actually did this before. I have this nice picture of water lilies or whatever they are, and there's like some pinks. I feel like there's areas in the image which I think would transfer really, really well onto here, right? So I'm thinking, okay, it must transfer, it must get these colors because they're so similar. How can they not transfer over? But what I end up getting when I did the transfer is, this is the original image. This is what I get after I do what I just did, basically, with the Euclidean distance. And I'm just like, no, that's not right. That's like so drab and brown and gray. It makes sense, actually. Well, it turns out that the RGB space is a good intuitive representation of color, but it's not a good perceptual one. What does that mean? So we have values of RGB as a value from 0 to 255. R is 0 to 55, G is 0 to 255, blue is 0 to 255. Now, although this makes sense, like to store it in data, but our eyes don't see it that way, right? Our eyes are kind of biased to certain. I think like greens are a lot more sensitive to our rods and cones inside the eyes. So although the colors in 3D space are very, very close to each other, our eyes don't think so. So this is the artifact of what happens when you trust the RGB space too much. It gets the closest color, but the closest color really doesn't satisfy your eyes. But mathematically, it's correct. What you really want is something like that, where it's not mathematically correct, but it's visually correct. So that's the whole idea. So other than RGB, right? So color, we know it as being represented as three values: R, G, and B. But there's different ways to represent colors. There's CMYK, which is used for like printing and stuff, or cyan, magenta, yellow, and key, or HSL, like hue, saturation, and lightness. That's also another way to represent color, right? So there's this hue wheel, which is kind of like this continuous wheel, and then the saturation, how vivid it is, and the lightness is how bright it is. And then there's also something called nonlinear color spaces. So what we've been talking about, like CMYK, HSL, and RGB, they're linear color spaces where one color is if this color is less than this color, this color is less than this color is less than this color in like a linear fashion. So you can form cubes and stuff. But there are nonlinear color spaces as well, like CAM, CIE, YUV, and in these color spaces, like the distances are not that obvious. It's not like you can. It's not like RGB where you can just like subtract things and it works out that way. There's like a curve and things like that. Things move in like a curve fashion. So perhaps we can find what we can do is we can convert RGB into a different color space and maybe do color transfer in that space. Or perhaps we can find maybe like a better distance calculation rather than just Euclidean distance. So I went looking for this actually, and I went across this website. It lists like this guy was working in color theory, and he was kind of like sad that the RGB color space is really bad at all these color transfer stuff. He's basically seen the problem I faced, but he likes the RGB space a lot because distances are very intuitive in RGB, but distances are more visually correct in other spaces. So he said maybe I can find like a distance that works, kind of like is a good trade-off between the two color spaces. So he details a lot of things on that website, which you can find the link here. But essentially, he boils it down into this very, very simple equation, quote unquote simple. But let's see what it is. So it says R bar here is the red channel of the first image plus the red channel of the second image divided by 2. It's the average of the reds, basically. So we have this average red color. And then we have our delta R, delta G, delta B, which is essentially what we did with Euclidean distance. And there's this big square root function down here, which is like, oh boy, I don't like this. But it's actually not that crazy. So do I have like a pen tool here? No, I don't have a pen tool here. Okay. Use your hands to cover this part of the equation, this number 4, and this part of the equation. If you did that, yeah, I wish I could draw stuff here. But if you did that, essentially, if you like block it out with your hands, all that's left is delta R squared plus delta G squared plus delta B squared, which is the Euclidean distance, right? Which is what we've been doing all along. So what this is saying is, it's just a different weighting of the Euclidean distance. We weigh delta R squared differently with this coefficient. We weigh delta G squared with with 4, and then we weigh delta B squared with this coefficient. So in this way, we can kind of like get a weighted color measure, which is more visually correct versus more mathematically correct. But essentially, we haven't run away from the whole idea of the Euclidean distance. We just weigh the Euclidean distance in such a way that we get better colors, essentially. So how he gets these values, well, you're going to have to read that blog post. But essentially, it's not such a big jump from from the Euclidean space. We just need to calculate these coefficients and we're done, essentially, right? So let's try and implement this. It's actually a lot easier than you think. He does give like an implementation of it in C++, but we can't use that. Essentially, what we're going to do is just change the Euclidean distance calculation that we've done already to incorporate this color distance thing. Okay. All right. I'm going to refer back to probably this equation because I like this one better. Or yeah, so he does some bitwise tricks here. If you follow the math, if you follow the math here, it's essentially the same as what he's doing over here. Okay. Alrighty. Let's go back to our distance calculation here. So the first thing that we want to do is find our R squared, R bar, which is the red, the average red channel, right? Now that's pretty simple. We just need to get YDA. I need to get all the values of YDA and just the red channel. 0 is the red channel. And I need to subtract all the values of XDA. So I'm going to call this R bar. Yeah. I'm going to say xdA minus yda 0, but I need xdA 0. That does not work. I think I can do this. Let's see. Whoops. Nope. Let's hide you guys for now. Let's have a look at our bar. Is that correct? I think that's correct. So 56969 by 30125, and it's just the red channels, I think. So essentially what I did here is I converted XDA into a one-dimensional vector, and then I subtracted it from a matrix. Yeah, and then it just becomes like a broadcasted approach, and then I get this, basically. That's good. And then I need to divide this by 2. Right? I hope I've done it correctly. Yes, I need to be careful because if I do divide by 2 here, it's going to convert it into a float type. I want to do integer division. That's very important to maintain the integer type. So int64. Perfect. So then I need my delta R, delta G, delta B. That's pretty easy. Oh, no, it's plus here, not minus. Plus 2. So let's calculate my dr, which is xdA all rows 0 minus yda all rows 0 to 1 divided by, no division, dr, and then dg db. So again, 1 here, 1 to 2 here, 2 here. Minus 2 channels of y and so on. Okay. Then what we need is this weight matrix, which I keep forgetting how to do. But if we follow this thing, it says we don't need the square root, but there's like 512 plus r mean times r bit shifted by 8. Yikes. Okay, let's just do that. So 512 plus r bar, for us it's r bar, but whatever. And then squared times r squared, for us is dr. And then it says shifted by 8. Bit shifted by 8. Okay. That's the first part. That's the first part. Plus, so let's just make a note. Weighted dr squared. And and then in the next one, it's very easy, 4. Just 4 times delta g squared. Delta g times delta g essentially is delta g squared, right? So I hope you can follow along. Weighted dg squared, and then weighted db squared, which is 767 minus r mean. My goodness, I don't know how these guys thought about these, but hey. Times b shifted by 8. Times b shifted by 8, and we're done. Okay, and this will be my pairwise, which is the sum. And if I have a look at the pairwise matrix, pairwise, awesome. That's what I expect to get. think that's good. Yeah, and then the rest of it is just all the same until we get mapping. Yeah. Okay, so we've implemented essentially this thing, which is from this equation, into Dask. And now Dask should be able to calculate for us this new mapping. So let's give it a run. Go and grab coffee, go watch another ad on YouTube or whatever. Wait for that stuff to run. And once it's done, we can create another mapping, another lookup table, and then transfer our new image. See if there's a difference or not. If there is, then great. If there isn't, well, there's just no good colors to transfer. Usually I see a subtle difference, and the difference usually makes sense, So, excuse me. Talking so much, my nose is getting wet. Alrighty. Cool. The mapping is done. I just need another lookup table down here so I don't mess around with the stuff up there. Okay. I should have the new mapping now. And I'm just going to copy this here. Okay. And then finally this. I just want to keep this image for comparison later on. Awesome. So this is the transferred. Okay, let's see if there's a difference. So this is using this perceptually better color distance. In some images, you see it a lot better than others. So let's see if there is anything particularly different here. Honestly, there's not really. Yeah, there's not really much of a difference. Yeah, I can't see much of a difference between the two pictures. I don't know if you guys spot anything, but did I calculate that right? Mapping is out. I did the mapping. Mapping is out. Mapping goes to here. I did the lookup table, right? 76 is the mapping. 93. Oh, no, I didn't. Did I do the lookup table? No, I already did the lookup table. Yeah, honestly, this image maybe it doesn't have much of a difference. I mean, should we try another image? What do you think, Shok?
Let's do the same image that you had at the very beginning, maybe.
Yeah, I can't find those images
Oh,
anymore.
okay.
I think it's in my other computer when I did this before. But
maybe the flower.
This? Maybe this to this. I feel like the comparison might be okay. Let's give it a try. Why not? Why not? Why not? So let's drag that in here and drag this guy in here. Go all the way back up here. I need Svetovaya, Palitra, 1943, and Svetovaya, 2023. Okay, pop. Image X looks like this. Image Y looks like this. So I can see a lot of similar colors. I wonder if there's going to be much of a difference. Well, let's see. Let's just skip all the way down to here. Set our XAs and DAs. Do our mapping. Whoops. Yeah, so sometimes Dask will tell you like, oh, because you have too many colors, I'm going to increase the number of chunks. But don't worry about it because it's going to do that automatically for you. And usually the factor doesn't increase that much unless you have a very, very, very big image. So here we see that we have 80,000 pixels and 40,000, which is a lot bigger than the other one. So it's increased the factor of chunks. But honestly, it doesn't really matter because it's still going to be in the order of hundreds of megabytes for each chunk. Sorry, hundreds of yeah, I think it's megabytes. Somewhere down the line, it's megabytes. So, yeah. So don't worry about those warnings and just run the mapping again. Okay, this one's taking a bit more time, but once it's done, we can just do this whole thing again. Okay, so this is the. I should maybe have another one where it does the good old normal one without the Euclidean distance without doing all this fancy stuff. DC is equals to, I think it's NP, no, XDA minus YDA reshape minus 113. Yeah, I think that's the only difference. And then, okay, let's call these things, see, this is why variable names are important. Let's call this Euclidean mapping, and let's call this cool mapping, right? Right. Okay, so that mapping is done. Well, I'm just gonna run it again because we've renamed these things. So I'm gonna call this Euclidean mapping is Euclidean mapping.compute. Let's run that. Yep, no problem. And let's do the same thing. I should have saved, well, too late now. Cool mapping and cool mapping. So now we have two, and we should have a Euclidean distance mapping lookup table. And also a cool mapping lookup table. Cool mapping. This is EUC. This is cool. Let me just run this as well. So it's all running. This is going to be our EUC image. Excuse me. And then copy all of this into here. And then this is going to be the cool mapping. There we go. And if I didn't mess anything up, I think it should be fine. Oh, this is taking a bit longer than expected, but I'm not surprised because there's quite a bit to compute. So actually, if I broken that up, would it have been faster? Probably not. I don't know. Probably not. I haven't tried actually. It's always good to kind of like check out these performances when you're doing these really big calculations, because sometimes breaking things down might speed up the computations in some cases. It's a lot faster here, so I'm thinking that breaking this up might make it faster. I don't know. I haven't tried it. Probably worth trying out. Okay. So I'm hoping to see something very interesting. If not, well, I wish I had that photo of the flower again. I can find it. It's online somewhere, but I wonder if it's in my my Windows PC here. If it is, then we can give it a try again, because
I think that would be fine.
honestly,
so hopefully this one will work because there is a lot
yeah,
of
hopefully.
purple and pink. So I'm pretty sure the mapping might become a little bit different.
I mean, for sure
So-
the pinks will transfer. I'm
Yeah.
not so sure
It'll
about the
be more
greens.
vivid.
Because there's no green here. Well, at least I can't see it with my eyes. So well, let's see. Let me just quickly jump over to my other computer to see if I can find those flowers or not. Because usually if it's in one computer, I don't move it around that much. And it's looking like it might be just on that computer. Yeah. Yeah. Unfortunate. Unfortunate. Anyway, transfer is done. Let's create our lookup tables and let's transfer. That's our first one. Okay. So pretty bad on the
It does
green.
look different.
Yeah. So let's
Very
bring
different.
out the original image Y for comparison. Bring it up here. So yeah, so you see, I mean, clearly all these yellows and stuff are, probably not there. The greens also are a bit faded.
But the pink was.
The pink's kind of vivid, right? I think it did pretty
Yeah.
well with the pink. So that's the Euclidean distance. Let's see what the cool distance gives us. Da, 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 da. Slightly different, isn't it? Is it just me, or is it just
I feel like something is not right. Is it? Because it almost looks the same. If you go back, aren't you supposed to square the whole thing, or you don't need to square the equation?
You know what? You're right. I do need to square it. Thank you for that. Good catch.
Yeah, I was wondering if that was the issue, because also the one below it also, are you supposed to square that?
No. I think that one.
Yeah, because he has
we
at the
do a
end
square root, but this r squared has to be squared. But I think I already do it squared. So I just calculate the difference here, right? I've done the difference here. And this is basically dr squared, dr times dr. So
Okay.
that's that part. 2 plus r, what's the 512 plus r mean? I'm pretty sure I got the r mean, right? Or did I?
So the r mean is basically the minus divide
perhaps
by.
I did not do it right. No, I think this is okay. Let me jump back to my code from way back because I know this one works because we did get very different transfers.
Because I'm wondering, because they almost look the same, so that's why I'm kind of a little bit unsure, because it happened twice, for the first one and for this one.
Right. Okay. Yeah, I'm gonna perform magic, but essentially I'm just copying code from from before. So yu, well, I guess I call it yda here, equals yda dot reshape into, I think this is where I went wrong. I'm supposed to do this reshape first, like I did here, but I didn't do it here. I think that's where I got it wrong. But let's continue. Yda all 0 plus xuda. Sorry, xda all 0. That's fine. And yda all 0. Yeah, I think that's where I went wrong. I think the calculation is wrong. Okay. So I'm supposed to do y minus x. So this is supposed to be 0, 1, 2. Oops. 2. And I actually need these guys to subtract x. Yeah, so delta R, delta G, delta B. The top one is fine. Pairwise is the same. Okay, so let's do this again. It's still giving me the same warning, so that's a good sign. I think it was the reshaping that did it, because I think
So
if you just took...
yeah, so I was gonna ask about the reshaping. So what you're doing here is that exactly.
I kind of explained it briefly when I was doing it down here, but let me just show you in the terminal while that thing is running. I hope that's big enough. Oops. I don't have IPython here. Conda activate torch. IPython. Okay. Smaller. So if I have a NumPy array, right now, let's say I have a 2D array, right? Let me just make a... do you have magic here? Oh, there's no magic square. Okay. Linspace, a range 9. And I reshape it to 3 by 3. So I have this X, right, which is just a 3 by 3 matrix, 0, 1, 2, 3, 4, 5, 6, 7, 8, right? Following so far? And
Yep.
I have another another matrix, which is just ones. Give me 6. I reshape as 2, 2, 3. Okay, and I have these 1, 1, 1. I want as okay, so I have this X and I have this Y. Let me do Y, all rows, sorry, all columns, second row. Okay, so I have my X, I have my X here, and I have my Y. Okay, so X is 0, 1, 2, 3, 4, 5, 6, 7, 8. Y is 1, 1, 1, 2, 2, 2. What I want to do is subtract 0, 1, 2 with 1, 1, 1, and then 0, 1, 2 with 2, 2, 2, and then 3, 4, 5 with 1, 1, 1, and then 3, 4, 5 with 2, 2, 2, 6, 7, 8 with 1, 1, 1, 6, 7, 8 with 2, 2, 2. That's basically doing delta RGB of x1 and y1, x1 and y2, x2 and y1, x2 and y2, x3 and y1, x3 and y2. So basically every possible comparison between each pixel, essentially, right? What I do in the code is I do y dot reshape minus 1, 1, 3. So this turns y into like a 3D matrix, right? So if we took at the take a look at the shape, it's 2 has 2 rows and then 2 of this 1 by 3 matrix vector. What that allows me to do is if I do then x minus y reshape, I can basically broadcast all the subtraction of 0, 1, 2 minus 1, 1, 1, 0, 1, 3, 4, 5 minus 1, 1, 1, 7, 8, 9 minus 1, 1, 1, and so on. And the same for 2, 2, 2. But if I just did x minus y, it will give me like, oh, look, they're different sizes. You cannot subtract matrices of different sizes. So what I'm doing is this broadcasting
Just reshaping it so it looks similar to the other matrix, so you can actually do the subtraction.
So the idea is this broadcasted subtraction is kind of like doing a for loop. Like I do for I equals to 0, j equals to 0, array 0, array I minus xi minus yj. sort of thing, right? So you have this quadratic thing. But rather than doing a for loop, which is usually slow, you can do broadcasting, which is very, very fast. And it's like tens of times, maybe even like 100 times faster. Probably not 100, but maybe tens of times faster. Yeah,
And that's
so
only
it's just
possible
like
through NumPy, right?
yeah, that's only possible to like any matrix library. It's called broadcasting, or like another term that they use is vectorization. If you can vectorize any,
I remember studying that part in university. It's been like 3 years. Last time I did anything with vectors. But I think I understand the concept, because I remember the way we used to calculate between vectors and how we did all these things. But yeah, this is pretty new for me. So thank you.
Yeah, you're welcome. So we hopefully get our new mapping now. Hopefully. Image Y, bad transfer. Let's hope for a good transfer, inshallah. Let's see. No, it's still the same.
Very
Is it?
interesting.
I think it's basically exactly the same.
Yeah.
One thing we could check is if the mapping is the same between the two. So if I have EUC mapping and cool mapping, are they the same?
They are exactly the same. Wow.
Well, let's see. Mapping. NP.all. If they're all the same, then there's something wrong. Oh, they're all the same? Okay, there's something wrong. I see why we got it wrong. I have a typo.
Oh. But it didn't throw an error. Why?
Yeah, because pairwise was saved from here, which I also use pairwise.
Okay. That's why we have to be careful with our variables.
Yeah. Yeah. Name your variables carefully, people. We make this mistake all the time.
Well, that's fine.
I'm pretty sure we're gonna get a better one this time.
So
I'm pretty sure, inshallah. But I'm pretty sure.
Have some expectations on that one.
Yeah. While this is running, let me just conclude the slides, and then that's pretty much it, basically. I've written a whole bunch more other things where I explored things like random walks within color space. That's something very, very interesting as well. Like if you walk around randomly, or if you walk to like neighboring pixels that actually exist, you get like this cool like high ISO increasing noise and that sort of thing. Yeah, that's more on the article that I wrote on Total Science. It's called The Perils of Palette Transfer. You can find it over there. Cool. You can find me on socials at Shaffers, GitHub, Twitter, Instagram. Pretty much everywhere I'm like at Shaffers. So that's like my global handle. And of course, my website, which is over there, shaffers.xyz. It's got like all the other projects I've done, all the other talks I've done. So if there's talks with videos, you can watch those as well. A lot of the stuff is like deep learning, machine learning sort of thing. This is like the more, not so hardcore deep learning. But the other stuff I've done is,
that was pretty cool, in my opinion.
So while we wait, because it's still going, we've got another couple of seconds. That's my website over there. So I've got like the stuff I've done with like videos and articles, if there are articles, talks I've done, data sets, and if you're interested, the publications I've done. Most people don't go beyond the bottom, so that's why I put that at the bottom. So okay. Bismillah. Cool mapping. No, we have to do this first. Cell 126. And yes, no, there's no difference. There's like very small differences, I think. There's like very minute differences. So I'm pretty sure they're not the same, or are they?
We could
Okay,
leave
let's
it at
compare.
that without you checking.
Okay, so it's not exactly the same.
Okay,
See,
then that's
the
correct.
mapping is not exactly the same. Is it
Very
better?
interesting.
Eh.
It's different.
It's different. I really wish I had
The
this
other
image.
flower, that's fine.
Yeah, these two image, it blew my mind. Like, can I just like extract these images? Yeah, do you guys want to
Yeah,
go and see if we could try, like, just
I
pull out
think I
these
think
images?
that's I think it's fine.
Yeah, you think
Well,
so?
people can try it on their own.
Yeah, you can try it on their own. On your own, just download these images from here, and I'm pretty sure you'll see there's like, oops,
Yeah, it's fine. It's
okay.
fine.
Uh,
Yeah, it's okay.
um, so, yeah, you can find me on socials over there, and yeah, I hope you've kind of enjoyed the whole thing. Although the palette transfer, I wish could have been better.
No, I think it's okay. Well, it still was a proof of concept, so it's fine.
Yeah, yeah. I mean,
It
it's
leaves room
not a
for
lot of code, as you
experimentation.
can see. As you can see, it's like, it's not
Yeah.
that much code. You have to be very careful with it.
Mm.
You know, variables and stuff, and the math stuff, the vectorization stuff is what puts a lot of people off. But once you get really good at this vectorization stuff, when you're doing anything like related to data science, you'll find so many avenues to, like, I can speed up this computation by like 10 times if I did it this way. And I also have an article on that on
Interesting.
speeding up computation using vectorization. Um, but yeah, there you go. So
Thank you so much.
maybe, yeah, you're
Yeah.
welcome. Let me just get back to the um, original screen.
Yeah.
I'm losing my
Uh,
voice. We have
yeah, you've
one
been speaking for 2 hours, I
attending
think.
who is,
Yeah.
wow, 2 hours? Oh my goodness.
Yeah, I think, yeah, it's been 2 hours, almost 2 hours.
Okay.
But
Uh,
that was a lot, and I think that was very interesting. Like, the recording is
Thank you.
still going, so
Okay.
even if people missed right now, they can still watch us later on YouTube.
Yeah.
Or on the page of the event itself as well.
Mhm.
But that was really interesting for me. It's a completely new topic.
Mm.
And now I need to study math again.
Honestly, I think the whole point is to just experiment with an idea that's crazy
Mm,
enough. Like, when
mm.
I went to do this project, I just wanted to do clustering, which is like the most basic thing you learn. This is like week 3 of machine learning, right? Um, I just
Well,
wanted
I
to
haven't
find.
tried week 0 for it yet, so this looks
Okay.
interesting.
But like something simple, and I had a lady who read my article recently, and she's been like very in touch with me,
Mm,
talking about ideas and stuff, and she's exploring like how can we compare the pixels even better than what we're doing now. So we've talked about like doing like Gaussians and all these like other machine
well,
learning avenues that really just spawned out of like a weekend project that I just wanted to try to see if it worked or not, sort of thing.
well,
Of
that
course,
is
there's
really
like
cool.
also the whole world of color theory, which I never actually cover. I know a guy who took 7 years to do his PhD just to come up with like a color map, which is now used by Matplotlib,
Wow.
the plotting library. So field of color theory, which is, well, I'll have to do a
Yeah, I think,
PhD on that, definitely.
well, inshallah. Maybe then you
uh,
can, I don't know, interview artists or people who are more in touch with the color theory part and things like that. I guess they would have maybe a different point of view on this, on like how you can use things like that in the future. Who knows?
yeah, yeah. I think the coolest thing that comes out when I first tried this whole thing was that early on, when you can just pull out like this palette, this small palette of like 16 colors, Remember that part where I had that square with like the
Yeah.
different colors?
Yeah.
So any image you can think of, pull it out. You can see it with your eyes. Like, I know this color is important. I know this color is important. How do I get those colors? You do k-means clustering, you get them. You know, it's one
Yeah.
very simple algorithm, and you know,
But it's so
the
satisfying.
yeah. And
Yeah.
you know, before I joined Khalifa University for my master's and now for my job, I was actually a front end developer for a local company here in Malaysia, and
Interesting.
I was always interested in like making things look thematic, you know. So I wanted one theme, so I always had to choose like a certain color palette, and choosing a color palette is never obvious for me. I always had to go to a website and like they would have color palettes prepared.
Yeah.
I always wanted to
Yeah.
create my own color palette just by what I see and like, you know, and well, 10 years later I did it.
Alhamdulillah. You
Alhamdulillah,
still
yeah.
achieved the goal. Now
Well,
what's
not
left
10.
is for you to go back into front end development.
Yeah, those days are behind me. I think I'm deep in the back end now.
Oh well.
All the ML and all the deployment stuff.
I think that opens another different topic for maybe a future feature for you to come and
Probably.
talk again. But
Um,
next time, maybe not during Eid.
probably another time. Yeah,
Yeah,
definitely.
inshallah.
Yeah, for sure. Please get in touch. You know my socials. Is there a way to like reach out to the people who missed it? Oh, I guess if they care enough to watch.
Well, we do have announcements, and we can actually what do you call send to all of the members who are in the GDG community
Mm-hmm.
and the GDG group, so
Yep.
we can broadcast that. So definitely.
Okay.
So nothing is missed.
Awesome. Awesome.
So yeah,
Yeah, that's pretty much it for me.
I think all right.
Sorry for the long journey. It's
No, that was definitely fun for me as well, and really thank you for showing up and giving us all this cool content. So
yeah.
thank you.
You're welcome, everyone.
Let's
So,
wrap up with a picture.
oh yes, please, of course.
Yeah, let's do this. One, two, three. Oh, wait.
No. Yes. No?
Okay. Yes, yes, definitely yes.
Okay. Awesome.
All right. Thank you, Shafiq.
Thank you, everyone.
And hope to
It's a
see you
good
again
night
with
for
us.
me. It's
Yo, yeah.
11 p.m. where I am in
Oh, wow.
Malaysia. 11:30 almost. So.
Yo. All right. I hope you have a good
All right.
sleep, inshallah.
Right.
And
Have a good
Eid
evening,
Mubarak.
everyone. That's Eid Mubarak as well. Thank you very much.
Bye bye.
Hopefully, I'm out of this quarantine.
Inshallah. Inshallah.